Okay. So in the previous session, we discussed phases and phase diagrams. In today's session, the next part of the session, that is the construction of equilibrium diagrams. So we'll discuss how to plot the equilibrium diagrams in today's lecture. So equilibrium diagrams can be plotted in various methods. So one of the popular method is called Cooling curves. So by using series of Cooling curves, you can plot the equilibrium diagrams. Now, first of all, the question always comes into mind, how to generate the Cooling curves. So in order to generate the Cooling curve, let us perform virtually very simple experiment called thermal analysis. So what we do in this thermal analysis technique is we will melt the alloy at above melting point, obviously, so that the alloy or the system for which we want to construct the cooling curve becomes molten state, that is in completely liquid state. Then what we do, we will insert the thermocouple, and the other end of the thermocouple we will give it to the temperature indicator, so that we can continuously see the temperature of the molten metal. And in order to form the cooling curve, we need to use the cooling rate such a low, so that we will try to achieve the equilibrium cooling. So in order to achieve equilibrium cooling, we need to go for very slow cooling. So in order to achieve this slow cooling rate, what we do, we will cool the alloy or the particular system in the furnace itself. If you want to take, let us take the example of lead and tin. And if you want to construct the cooling curve for 20% lead and 80% tin, so we will melt this lead tin mixture into the small crucible in the furnace. After melting, obviously we can see the temperature of this molten metal via thermocouple to the temperature indicator. Then do not open the door of the furnace. So close the door of the furnace and switch off the furnace and cool the alloy in the furnace itself. Now in this particular scenario, what we do, or in this particular situation, we need to record the different temperatures at different time periods. So we will make the two columns. The first is the time and second one is the temperature. So for every 1 minute interval, we will record the temperature drop of the alloy. Suppose initially it is a 200 degrees centigrade. So that is at 0 seconds we have 200 degrees centigrade. Then after 1 minute interval, observe the temperature drop or the temperature of the system, and continues these readings up to solidification. Now we have two column data. The first column is the time and second column is the temperature. And if you plot this time and temperature data, you can see you will get this curve, and this curve what we call is a cooling curve. Okay, so this cooling curve you can see, so here, so this portion we call liquid and this portion is solid, means above point B alloy is in or the system is in liquid state, below point C system is in solid state. In between these two, you can see here it is a liquid plus solid portion, means at a constant temperature alloy has solidified into solid state. So you can see B to C is the region at which your alloy continuously solidifies into solid state. But you know, remember here in this particular situation, so at constant temperature this particular system has solidified. Whereas you can see the second curve. Obviously, above point B we have liquid, above point C we have solid. In between B and C we have liquid plus solid region. You can see liquid plus solid region. It is a semi-solid region, liquid plus solid. and alloy has solidified over range of temperature. So means solidification will start at this point and solidification will end at this point. So in between these two we have liquid plus solid. So means this point, so BL point we call liquidus temperature line, liquidus temperature point, and this point C we call solidus temperature. So from this thermal analysis experiment we can obtain liquidus temperature and solidus temperature for different alloy. Suppose if you want to construct the equilibrium diagram for lead tin system, let us take first of all 100% lead. Keep the lead. So first of all, place the lead, pure lead, 100% lead into the crucibles. Commonly used crucibles are graphite crucibles. Place into the furnace, heat it around 200 to 220 degrees centigrade. It will melt. Then measure the temperature drop by different time intervals, and you can plot the cooling curve. So you will, after getting the cooling curve, find out liquidus temperature and solidus temperature. So the liquidus temperature is above which alloy is in liquid state, and solidus temperature is below which your system or your component is in solid state. Next carry out experiment for 20% lead, 80% 20% tin, 80% lead. Similarly, find out liquidus temperature and solidus temperature. Next, you carry out experiment for 40% tin, 60% lead. Again, find out liquidus temperature and solidus temperature. Like that, up to 100% tin, 0% lead. So you have started the experiment from 0%, 100% lead to 100% tin and find out liquidus temperature and solidus temperature. Now you have liquidus temperature and solidus temperature of all the alloys starting from 100% lead to 100% tin. Now join all the liquidus points and join all the solidus points. You can see here, you join all the liquidus points and join all the solidus points. Similarly here, join all liquidus and joins all the solidus points. So this curve, what we obtain, you can see here. So this diagram is constructed for copper nickel system, not for lead tin system. And all the liquidus and all the solidus points for copper nickel systems are joined. And you can see you can obtain the curve. And this diagram or this curve we call as an equilibrium diagram or phase diagram. So by using series of cooling curves, we have obtained this diagram, and this diagram we call equilibrium diagram, constitutional diagram or phase diagram, all are same. You can see, so this copper nickel system diagram and this diagram is different. So this copper nickel system diagram we call is a binary isomorphous system, because we know that in case of copper nickel, all the Hume-Rothery rules are satisfied. Whereas, so in this particular scenario, you can see the lowest melting point is observed for this particular component A and B at around 40% B. You can see lowest melting point is observed. So this diagram is a eutectic type diagram. Whereas this is a binary isomorphous system and this is a binary eutectic type systems. So by using this thermal analysis experiment, phase diagrams can be plotted. So phase diagram, a map based on a system's free energy indicating equilibrium system structures as predicted by the Gibbs rule. As you can see it here, so this is a copper nickel type system provided here, copper nickel type system. We will discuss more about phase diagram in this particular slide. If we know temperature and composition, then we know the types of phases present in the system. Example is that point A, temperature is 1100 degrees centigrade and composition is 60% weight percent nickel. So this is a copper nickel system. You can see two vertical axes. So this is 100% copper, 100% nickel. This is a percentage of nickel increases from right to left, left to right, and this is the temperature axis. So at point A, temperature is 1100 degrees centigrade and composition is 60% weight percent nickel. At point B, temperature is 1250, that is 1250 degrees centigrade, and composition is 35 weight percent nickel. But here two phases are present. At point A, only one phase was there, that is only solid phase, that is alpha. But at point B, you can see two phases are exist, liquid plus solid, so two phases. And rule number 2, so what information we can draw it from the phase diagram is that if you know temperature and if you know composition, we can find out the composition of each phase. For example, again we will consider the example copper nickel system. At a 35 weight percent nickel, you can see, so for 35 weight percent nickel, at the point A, we have only one liquid phase and composition of this liquid phase is 35 weight percent nickel. So only liquid phase, so that's why composition equals to 35 weight percent nickel. At the point D, we have only one phase, that is solid, so that's why again the composition of this solid phase is 35 weight percent nickel. But at the point B, we have two phases, liquid and solid. So composition here at this point B of liquid phase and solid phase is different. And this composition of liquid and solid phase can be determined by using a tie line. So tie line can be drawn from this point B up to it will cut the liquidous line and up to solidus line. So we can see here we have drawn the tie line, and this tie line is we have extended up to liquidus curve and up to solidus curve. Now find out the composition corresponding to this liquid region, liquidus line. So find out the composition corresponding to this point, that is 32 weight percent nickel. That is the composition of liquid. Similarly, find out the composition of this tie line we have extended up to solidus line. So corresponding to this point, find out the composition, that is 43 weight percent nickel. That is the composition of solid phase. So means by using the tie line, we can find out if two phases are there, then from that one particular point which is of interest, in our case 35 weight percent nickel and temperature 1250. Obviously, in order to locate point B, you should know the alloy which is under investigation and temperature which is under investigation. So by locating point B, just draw tie line which will up to or extend the tie line up to liquidus line and solidus line, and find out the composition corresponding to liquidus line and solidus line. You will get the composition of liquid phase and composition of solid phase respectively. So here composition of liquid is 32 weight percent nickel and composition of solid is 43 weight percent nickel. By knowing composition of liquid phase and composition of solid phase, again the question comes into mind at a point B. Here at point B, what is the percentage of liquid phase present and what is the composition of solid phase present? Remember that by using tie line we have drawn the compositions. We have determined the compositions of liquid phase and composition of solid phase. But we don't know, still we don't know what is the percentage of liquid phase present there and what is the percentage of solid phase present there. In order to find out the percentage of or the amount of phases present, we need to use a lever rule. So lever rule. So a tie line connecting the phases in equilibrium with each other at fixed temperature, so called isotherm. But how much of each phase we can think of it is as a lever, so to balance. So lever rule is just like fulcrum which we play into in children days in our garden. So it is we can think of it as a lever so as to balance. So this is a small expression which is a derivation which is given in this slide. I will not go into the more detail because it is very simple to understand. You just look at this, and obviously I'm going to upload this presentation on Google Classroom. Again, you can download it from there and study it. Now here you can see directly we will use the lever rule. If we know temperature and if you know composition, then we can find out the amount of each phase present. Let us take this similar example or the same example, that is 35 weight% nickel. So composition of liquid and composition of solid is determined. So you can see it here. At A, 100% liquid, so 100% liquid phase. At the point B, 100% solid, so 100% alpha. But at point B, two phases exist. So how to find out percentage of liquid phase and percentage of solid phase? So we have determined composition of liquid and composition of solid. In order to find out the composition of liquid phase, what we will do? So 43 minus 35. 35 is the alloy which is under interest. So 43 minus 35 divided by 43 minus 32. In order to find out the percentage of liquid, we will use this region. So that is the balanced region. In order to balance this fulcrum, we will consider this part, that is 43 minus 35 divided by 43 minus 32. You will get percentage of liquid phase, that is 73 weight%. And in order to find out percentage of solid phase, what we will do? So 35 minus 32 divided by 43 minus 32. Remember that denominator remains same, only numerator changes. So we will get 27%, or 100 minus 73 can be done in order to find out the balanced phase. And that balanced phase is obviously here in our case is a solid phase and percentage is 27%. So by using this lever rule, amount of each phases can be determined.